Welcome back to differential equations. In this video, I want to talk about exponential models. I fully expect that you've seen the idea of exponential growth and decay in a previous course, probably pre-calculus or maybe college algebra, however it was called wherever you established it. But in this video, we're going to look at the calculus definition of an exponential model, which is going to look very different. In essence, when you've encountered this before, somebody has already done the differential equations work for you, and now I want to show you where it comes from. All right, but an exponential model is a proportion. Specifically, it is saying that the rate of change of some amount, so n prime as a function of t, is proportional to the amount itself. The more there is, the faster it's changing. Classic examples of this are bacteria growth. Bacteria grow by cutting themselves in half every so often. The more bacteria there are, the more likely it is that one is going to cut itself in half. Radioactive decay. Radioactive decay works by oversized nuclei splitting themselves in half every so often. The more nuclei there are, the more often it's going to be that something gets split in half. All right. But in general, when you're working with a proportion, you can turn it into an equation by simply introducing some constant of proportionality, which we almost always represent using the letter k. If k is positive, we're going to call it a growth constant. If k is negative, we're going to call it a decay constant. All right, but this is a differential equation. And in fact, if I get my head out of the way, this is a separable differential equation. It's kind of boring as separable differential equations go because it doesn't have an independent variable showing up at all. But I can still solve it by direct integration. Remember, n prime dt, well, that's just dn. So we have the integral of dn over n is equal to the integral of k dt. Integral of dn over n is going to be the natural log of the absolute value of n. Integral of k dt is going to be, well, that constant times t, plus an arbitrary constant of integration. It now feels like we have two arbitrary constants in the equation, but remember there are different reasons. K is the constant of proportionality, C is the constant of integration. We are much more likely to quickly be able to come up with a value for C. K is going to be a property of the situation we're studying. All right, but then from here, the same tricks. If I want the absolute value of n by itself, that means I'm going to have to raise e to the kt plus c power. I'm going to split that off. I'm going to deal with the absolute value, and I'm going to say that all this stuff in front is an arbitrary constant. All right. In general, we'll call that A, although for reasons that will make a lot of sense in just a moment, it's often written as n sub 0. Well, if you evaluate this function at 0, you're going to get n sub 0 times e raised to the 0 power. E raised to the 0 is 1. Anything to the 0 power is 1. And so that's where the name comes from. N naught is n of 0, the initial value of the thing we're dealing with. That will always be the case. You don't have to put it in as something special. But this should be far more recognizable to you as an exponential growth or decay model. Now you understand where that formula comes from, but the applications are the same as what you've seen in the past. In a certain radioactive sample, 4.2 grams of the radioactive isotope decays into 3.0 grams of that isotope and 1.2 grams of other elements after 7 days. Find the decay constant. Well, setting this up as a model, we know that radioactivity is exponential decay. N of t is equal to n naught times e to the kt. We also know, because it's decay, that k should be a negative value. Some people like putting the negative in the equation. I've always been a fan of k is a negative number. Mathematically, they're equivalent. Either one does work. Right? Initially, we have 4.2 grams. After 7 days, we're down to 3.0 grams. So n of 7 is equal to 4.2 times e to the 7k, and n of 7 is 3.0. This is math class, not physics class, so I'm going to stick with fractions, although this is definitely one of the few places in the course where if you grab a calculator and do a decimal approximation, that's fine. But 3.0 over 4.2 is the same thing as 30 over 42, which is a fraction that reduces to 5/7. So the natural log of 5/7 is equal to 7k, which means that 1/7 times the natural log of 5/7 is our value of k. As far as I'm concerned, that's the best way to write the answer. But I'm a mathematician, and mathematicians tend to be crazy about these sorts of things, so you'll probably end up putting that into a calculator. You get negative 0.048, etc. as a decimal approximation. The doubling time of a bacteria sample is the time it takes for the number of bacteria in the sample to double. Mathematically, we can write that as n of t sub d is equal to 2 times n naught. I would like you to write an expression relating the doubling time to the growth constant. All right, so I think by context, you can pretty clearly assume that bacteria growth is an exponential growth, but here's me explicitly saying that. There's no numbers in this problem, it's just a bunch of variable manipulation. It might be something you've seen before, but if not, I want you to play around with it and see if you can figure that out on your own. All right, we'll see what you can do with that one, and I'll see you in the next video.